Good afternoon, all. I am Dr. Harikrishna Gandam, Assistant Professor, National Rail and Transport Institute. Today, I am going to deliver a lecture on transportation models, quantitative methods. In short, it is called as TMQM. And in this particular subject, we are going to talk about the course outline. The course outline consists of introduction about the particular lecture, and then what are the course components, what are the objectives of this particular course, and then we'll focus on the course and an evaluation process and then the reference given for the particular subject. And also today we are going to focus on module 1. We'll talk about the probability and statistical application in transportation engineering. It covers the fundamentals of probability and statistics and the relevant applications in transportation. And in the module 2, we'll talk about traffic flow theory and model basics. How the transportation technology students going to study about the traffic flow theory as well as the related analytical models. And in the module 3, we are going to talk about the traffic flow planning models, which essentially comprises of 4-stage transportation planning process. And the subject also consists of other concepts and numerical methods. So the student will have the idea on the applications of these models and the theories that we discussed in particular subject. And when it comes to the course outline may consist of the traffic flow theory concepts as well as the traffic flow fundamental concepts initially. So the traffic flow theory is all about the knowledge of traffic flow characteristics and analytical techniques, which is essentially used in planning, design, and operation of transport. As a transportation engineer, the applications of traffic flow theory are vast. Essentially, the planner has to know the performance of the traffic flow by using shock wave theories, queuing analysis, capacity and level of service diagrams, and so on. And the transportation design engineer will use some fundamental concepts of traffic flow for understanding the designs are accurate enough. And then when for the daily operations of the transportation systems, we have to know where the bottleneck appears on the network and where there is a constraint on the road given network and so on. That can be dealt accurately or effectively using traffic theory concepts. So as a transportation engineer, we have to aware, it shows that we have to aware of the traffic flow theory and fundamentals. So initially we'll focus on traffic flow characteristics such as time headway, flow, space headway, density, and so on. And when it comes to analytical techniques, supply demand modeling, capacity and level of service analysis, shock wave theory, queuing models, and simulation. So this will be the part of the module 1, and which will talk about like student will have an idea about traffic flow characteristics as well as analytical techniques used by different agencies. And when it comes to the traffic concept, as you show in this particular picture, it will consist of a kind of this lane discipline, and we can see that almost 99% of traffic consists of cars. It's a cars only traffic. Very few trucks are observing on the road and also some light commercial vehicles. So in this kind of lane discipline scenario, we can easily interpret what is the headway of two vehicles or what is the total number of vehicles occupied the lane or the total road width, and also what are the speeds of the vehicles, whether it is a microscopic and macroscopic and so on. So by understanding the fundamentals of the traffic flow, we'll try to get the overall picture of the traffic flow. The overall picture in the sense here we can get the capacity and the flow as well as the level of service of the particular traffic stream and the delays occurring on the road and congestions happening on the road and so on. So these things will be covered covered in the under this particular chapter. So the outlines of this particular initial discussion is the flow rate, spacing, headway, speed, and density, and then followed by the relationship between these individual variables and followed by some examples. And we have some definitions essentially for speed. What is speed? What is the space mean speed, time mean speed, and so on. And the volume, we have traffic flow rate, traffic flow, and then different other volume related concepts. And the density is nothing but number of vehicles per kilometer. We'll see that how the density will be measured also. And then the relation between the volume, speed, and density. Speeds are, as mentioned, there will be different types of speeds. We have a space mean speed as well as time mean speed. And when it comes to the flow rate, the number of vehicles passing some designated roadway point in a given time interval, Q is equal to N by T. N is the number of vehicles, T is the travel time. How much time that you consider for counting the number of vehicles. So the units are typically vehicles per hour, or flow rate is different than value. Here, spacing can be two types. One is the distance spacing and time spacing. Initially, we will focus on the distance spacing, that is a bumper to bumper distance at a given point of time. That is called the distance or space headway. And we have time headway, which will be measured in seconds, which will be the stipulated time between two vehicles when when the first bumper cross the point, the next vehicle bumper cross. So the measured time T is equal to individual summation of all the individual headways, and the flow is equivalent to the number of vehicles divided by the summation of all the headways. So there we can obtain the relation between the flow and the time headway. Here, when you are obtaining a macroscopic quantity, that is a flow rate or flow, then we are relating that macroscopic quantity with the microscopic quantity, the HI. When you are summing up and dividing with n, you will get the average headway of the vehicles using that facility at a given point of time, correct, over the period of time. So Q will be relate with the microscopic content, that is H value. So Q is proportional to, inversely proportional to 1 by H dash. So that is the relationship that exists between the flow rate and the headway. And we have some headway distributions as well. We can obtain different distributions for different lanes, and also sometimes we can club up all the data and then get one distribution for the overall road width. So in case of lane discipline scenario, we have lane 1, lane 2, and lane 3, and so on. So when you can measure the individual headways and you can plot the histogram on the XY plot, like frequency versus time headway, then you can obtain some distribution. Or this can be used, like this can be represented by using some mathematical distribution such as exponential or normal distribution or L-long distribution and so on. So these things, the fitting of headway data using some mathematical modeling is important in microscopic simulation, where vehicle behavior can be simulated or vehicle behavior can be mimicked. And then we have a speeds as two types, time mean speed and space mean speed. Time mean speed is arithmetic average of speeds of all the vehicle classes, and space mean speed is the harmonic mean speed of vehicles, which are like the harmonic mean speed of vehicles using the facility over specific distance. And then space mean speed can be, as mentioned, is the harmonic mean speed, and will be mentioned using this particular relation. U is equal to sigma I is equal to 1 to n Li. Li is the individual distance traveled, which will be equal for all the vehicle classes divided by T dash. So this is the harmonic mean speed of the vehicle classes, and then space mean speed is always less than the time mean speed. And then followed by time mean speed versus space mean speed, where there is a typical relation between time mean and space mean speeds. On the x-axis, we can see the time mean speed. On the y-axis, we have a space mean speed. So in the absence of one, you can use the other relationship for obtaining the unknown values. If I know the space mean speed values, I can obtain the time mean speed value. From this graph, you can clearly see that both have a good relationship. That there is a good correlation between space mean speed and time mean speed. And the next point is about density, which is another important variable which will be used for representing the traffic flow. Here, the density is number of vehicles occupied given length of the road section. So here, the density units can be number of vehicles per mile or weight number of vehicles per kilometer and so on. So the density K is equal to N by L or Q by V. So the density can be measured directly or using already known variables such as Q as well as U. That is what we are trying to represent over here. There is a kind of relationship, other concept like free flow speed, geom density, and the capacity, and the related equations are also provided over here. And then we have some relationship exist between these variables, macroscopic variables. So these relationships are provided by Greenfield. So these Greenfield equations are mentioned over here. Like the first relationship is between the speed and the density. So here we use two parameters such as free flow speed and geom density. So that is what mentioned over here. So there is a linear graph representing the relation between the free flow speed and the geom density. Or you can simply mention it as speed versus density of the vehicles using the facility. And then we have several other curves which are representing the varying behavior of vehicles. And it is not all times possible to explain the relation using a linear graph. There is a kind of exponential relations also exist. And we have the flow versus density relationship as well. So as mentioned earlier, Q is equal to KV relationship. That is a fundamental relationship of traffic flow. Here, instead of V, if you substitute VF into 1 minus K by Kj, you will obtain this particular relation. Q is equal to UF into K minus K square by Kj. So the flow versus density relationship as per the Greenfield is a parabolic. So on the x-axis, we have a flow, which is mentioned in terms of vehicles per hour. On the y-axis, we have a density, which is the number of vehicles per hour. So this is about the another relationship versus flow versus density, which is parabolic in nature. In this particular graph, you can observe uncongested flow, congested flow, optimal density, and optimal flow. And we can obtain the trajectory, like the transition of this particular curve as well as the tangents and secants of the particular curve, which will be give you the shock wave speeds, as well as the average speeds over the process. So this is the two-regime traffic flow condition compared to single regime. There is a difference between single line and the two lines which are showing over here, which will be developed by different researchers, or you can say that they're suggested by different researchers. So this is called two-regime condition, a separate diagram for free flow condition and congestion condition. And we have speed flow relationship as well. In this case, like we can also obtain same fundamental relationships of traffic flow and the relation between U and K. We can obtain the relation between speed and flow as well. The relation between speed and flow also a parabolic one. In this case also, we can see the regimes, two regimes. One is uncongested flow and the congested flow. And also we can observe the free flow speed where flow is almost nil on the road. And when there is a point called optimal capacity, which will be obtained at optimum speed and zero flow on the road. So this is about the relation between speed versus. So for this is a discussion for today's, and we'll continue in the next for the remaining things. Okay, thank you so much for your patience.